Let's talk about capacitors in an AC circuit. We talked about resistors and inductors. Let's bring capacitors into the mix. We can use the Kirchhoff loop rule again to give us an expression for voltage in a capacitor. And we see that we can write this as delta V max sine omega t for the voltage across the capacitor at any time. Not a big surprise. Let's see where it gets a little bit more surprising, because what we're going to want to do is talk about the current. So first of all, we know we can write that the charge at any time is C times the maximum voltage times sine omega t. I've got to take a time derivative to find the current at any time, though. And in that case, if I take the time derivative, I get a cosine term, or sine omega t plus pi over 2, if you will. And that is to say that the current is pi over 2 radians out of phase with the voltage. Same as the case with the inductor, except for the fact that in this case we're going to see that the current is actually leading the voltage instead of lagging the voltage by 90 degrees. In this case, the current reaches its maximum value a quarter of a cycle sooner than the voltage does. So we say that the current leads the voltage by 90 degrees in the case of a capacitor, which finishes our sort of slogan here, Eli, the Iceman. This is how you can remember how this works for inductors and capacitors. In the case of inductors, the EMF leads the current by 90 degrees when I have an inductor. The EMF lags the current by 90 degrees when I have a capacitor. And the way that people tend to remember it is a silly little phrase about Eli the Iceman. And you can see on here how they are both out of phase with one another. We can also draw a phasor diagram. In this case, we see that the current is leading the voltage by 90 degrees. Remember the case of the resistor, the two vectors were aligned, or two phasors were aligned. In this case, they're 90 degrees out, and instead of being like inductors, where the voltage and current are switched, capacitors look like this. The current leads the voltage by 90 degrees. Okay, so we see the distinction between inductors and capacitors. But like inductors, we can talk about a capacitive reactance, which is like a resistance term. In this case, we define the capacitive reactance as 1 over omega c. We use the chi sub c, or capital X sub c, to indicate capacitive reactance. The units, again, will be ohms. And we can calculate that in the case of a capacitor. We can find the instantaneous voltage as V max sine omega t, or I max times the capacitive reactance times the sine of omega t. And as you see, as the frequency approaches 0, in this case, chi sub c or x sub c approaches infinity, and the current approaches 0. So it's the exact opposite way that it works like an inductor does, an inductive circuit. So in this case, when x sub c approaches infinity, it looks like we have a DC voltage, and the capacitor would act as an open circuit. We can do an example of a purely capacitive circuit. Suppose we have the following. Suppose I have an 8 microfarad capacitor, and it's connected to a terminal with a VRMS of 150 volts with a frequency of 60 hertz. And we want to find the reactance, and we want to find the RMS current. So the reactance, the capacitive reactance, is equal to 1 over omega c, which is 1 over 2 pi times 60 hertz times 8 times 10 to the minus 6 farads. And that will give me a reactance of 332 ohms. My RMS current will just be equal to my RMS voltage divided by my capacitive reactance which would be 150 volts divided by 332 ohms, or 0.452 amps. So it's another very simple example of how to use capacitive reactance in finding RMS current. Well, of course, it wouldn't be any fun unless we could put all these circuit elements together. Let's look at the nice RLC series circuit where we have a capacitor, we have an inductor, and we have a resistor, all in the same circuit. And let's look at the behavior of the circuit. Of course, you can, as you would expect, depending on the sizes of the resistances, the inductance, and the capacitance, the circuit is going to behave differently. Let's look at that thing a little bit closer and see what happens. So, we have an instantaneous voltage, of course, of delta V max sine omega t. We have a current given by sine omega t minus phi, where phi is the angle, the phase angle between the current and the applied voltage. In this case, we have a situation where we have an inductor, a capacitor, a resistor. The current at all points in the circuit will have the same amplitude and phase, but we just have to figure out what that phase is. And that will be a little bit more involved because of the fact that in capacitors, the current leads the voltage. With inductors, the current lags the voltage. And with resistors, it's right in phase. So as you can see, in this relationship, we have the voltage for the resistor, the voltage for the capacitor, and inductor and voltage for the capacitor, all plotted versus the voltage, the current in the circuit. You see the current and the voltage across the resistor completely in phase. The current is lagging the voltage across the inductor. The current is leading the voltage across the capacitor in this diagram. And so the fact that you have those three things going on means that we're going to have to find a nice relationship between those equations. You can see the three voltages that we have, and they relate as sines and cosines, as we've said before, putting them all together. And so we can say that, first of all, the maximum voltage across the resistor is I max times R. Maximum voltage across the inductor is I max times the inductive reactance. And then, of course, same thing for capacitance, I max times capacitive reactance. When I add those three together, I should get the voltage coming out of the AC source, because what's dropped across one isn't dropped across the other. But if I add all three of the drops for capacitor, resistor, and inductor, all of that should be equal to what's coming out of the battery. Now, the problem is, though, it's not quite a simple addition because the phase relationships are different, so I can't just add them directly. So let's have a look at what we can do. Let's look at the phasor diagrams again. We can use phasor techniques for these three cases. So in the case of the resistor and the voltage and current are along the same line. Voltage leads the current for the inductor. Current leads the voltage for the capacitor. And so what we're going to end up doing is drawing a sort of composite of these three graphs depending upon the values of the voltage across the capacitor, the inductor, and the resistor. We do it the following way. I plot the voltage across the resistor across the x-axis. I plot the voltage across the inductor along the positive y-axis, and the voltage across the capacitor along the negative y-axis. I take the difference of these two voltages, voltage across the inductor, voltage across the capacitor, to come up with one of my phasors here. In this case, the voltage across the capacitor is voltage across the inductor is larger than that across the capacitor, so I have a phasor that's pointing along the positive y-axis. My voltage across the resistor, of course, is always on the positive x-axis, and I do essentially what amounts to a vector addition. And so the resultant vectors, the addition of these two vectors, gives me a vector at this angle with respect to the x-axis, the angle phi. That is the phase angle. And I can find that very simply by taking I can say that the tangent of this angle is going to be equal to delta VL minus delta VC divided by delta VR. And that will take the arctan of that value, and that will give me the angle phi, or the phase that is between these guys. We can show it another way numerically. The same thing is going to work for when I do it for the voltage. I can write it as I max R squared. These are the voltages across the inductor and across the capacitor squared, and then finally getting a maximum voltage equal to this quantity here minus, times rather, the maximum current. Now, we define this quantity, R squared plus X sub L minus X sub C squared, as the impedance of the circuit. Again, that's a unit of, it has units of ohms just like resistance does, but it's sort of a way of incorporating not just the resistance, but the reactance due to the inductor and the capacitor in the circuit. And it has units of ohms. Ohm's law essentially would say, in this case, my maximum current would be equal to my maximum voltage. Instead of divided by R, it would be divided by the impedance